Okay. Okay.
All right. 4 more talks to go before we head out for lunch. And we're starting off with Emanuel de Lima, who will tell us about non-chaotic classical transitions. All yours.
Okay. Thank you. Thank you for being here. And thank you also the organizer for this opportunity. Okay. So I'm going to talk about this non-chaotic classical transitions. And this work is, I have 2 collaborators in the Unesp of Rio Claro, Ricardo and Murilo. Okay. I will try to explain what I mean by non-chaotic classical transition. First of all, I will talk about chaotic transition, and then reach the non-chaotic ones. Okay. I will start by a sentence that I heard from my former supervisor, who used to say that chaos is more a rule than an exception when we talk about differential equations, and that always in my mind. But chaos, okay, it appears everywhere, but we have also the non-chaotic part, so we cannot forget about this. Okay. So the aim of this work has to do with control of process in atoms and molecules. Okay, but here I'm dealing with classical from the classical perspective. Okay, but of course, control of atoms and molecules has to do with quantum mechanics. Okay, but in this context, it's worth to point that classical mechanics can predict a lot of things, a lot of stuff in this context. There's I might say a strong correspondence in many situations between classical mechanics and quantum mechanics. So in many aspects. So this is why I'm approaching this problem by the point of view of classical mechanics. And one of the interests is also to know that what is the implication of classical chaos in the coherent control of atoms and molecules. There are recent works dealing with the appearance of coherent control in quantum chaotic systems. This work, if I'm not wrong, it's about the rotation of molecules. Okay. Okay, let's set up the problem. What I am interested is in make a transition. Okay, a transition between different states or different energies in a system. Okay. This is what I mean about this transition. It's population transfer. We are initially in a given state and want to reach another state. Basically, this is the basics. Okay. I will consider for short in this presentation just a one-dimensional Hamiltonian. And this transition, I might say that the initial energy, it's of the system Hamiltonian. It's H0 or H0, which is, you can think about as an atom or a molecule. And this system interacts with, for instance, a laser field with a dipole coupling. And by means of this interaction, it can make this transition, going from, for instance, from one eigenstate to other eigenstate of the original Hamiltonian. Usually, I will do research a pulse, a laser pulse that can make this transition. Okay, an external field that starts in a given time and is turned off in a later time. Okay. So I will specify a model here that I'm dealing with. We can generalize several results that I'll talk about here, but it's easier to follow to fix in a specific model. Okay. So the model I'm talking about is the Morse potential. It's a model for the vibrations of a diatomic molecule. You can see the potential at your left here. So we have inside the well, the molecule can vibrate. This is in the, you can see it's the interatomic distance. So inside the well, it can vibrate. In the corresponding movement in phase space, it's a closed curve. Okay, and eventually, if some transition is made to outside the well, the molecule it's considered dissociate. This is a very, although simple, one-dimensional, it's very interesting model because we can study vibrational excitation inside the well. We can study the escaping of the trajectories, which means to study dissociation. And also, we can study the trapping of trajectories initially outside the well and the transition to into the well. So it's this trapping by means of a laser field. It's known as photoassociation. Okay, and of course, the unbound trajectories are the outer trajectories in phase space that you can see. So this is the model I will most talk about here. So how people study this kind of model? This model has been a subject of a large bunch of studies during the 80s and the 90s. Here I select the paper just to summarize, but there's really dozens of many works on that subject, which is the most of them is interested in study the dissociation of the Morse oscillator. You start in the given vibrational state or a given energy, and you turn on a laser field with a harmonic laser field, for instance, and you can drive the transition for the trajectory escape from the potential. Classically, what happens is that several nonlinear resonance appears in the phase space. This is here a Poincare section, for instance. Here is the angle variable and the energy. You can see these islands, these resonance islands. Okay, and outside the resonance, several high-order resonance and a chaotic sea around. And the idea is the following. You put the molecule is initially in a given state, a given energy, and when you turn on the laser or the pulse, several islands appears, and if this the amplitude of the field increase, the island also increase. Eventually, the islands overlap each other, and the invariant tori between the islands just disappears, and you have a chaotic sea where the trajectories can move around. So if the initial state is in this chaotic sea, the trajectory can just escape from the potential well. And then just move outside the well. So this is one way of controlling the dissociation. So you just plug in the laser, you increase the amplitude, and by means of this chaotic, this diffusion in the chaotic part, you can dissociate the molecule. Interesting, there's a lot of correspondence between this classical calculation between the quantum calculation. For instance, the threshold for dissociation, the classical one, agrees with the quantum ones. But if you want to make a transition between a given initial state and given energy and another energy, you can do the following. You can select the frequency of the laser to trap the trajectory, for instance, in a resonant island. Okay? And you can chirp the laser so the resonance island can move around and possibly, for instance, raising the energy. So you can control transition between two states in that way. But if you want just to dissociate, you put in the chaotic C and it will escape from the well. Okay? This is all the research in that area started in these grounds. Okay, so more recently, but 10 years ago, there was also other proposal for controlling population transfer. This is the same model, also the Morse potential, the driven Morse potential. In this is another idea for controlling transition, dissociation, and so on. The idea it's a little bit different from the previous one. In that process or that mechanism, the starting point is the upper panels. It's to put the initial trajectories not on the resonance, but in fact on the separatrix of the resonance. You made the things so that the initial state is right on the separatrix. And here they use a Gaussian profile for the pulse. So they start with lower intensity, increase the intensity, and then lower the intensity again, the amplitude of the field. So the upper panels are they're increasing. It's a Gaussian profile. So increase, and the peak amplitude is the middle panels, and then they lower again is the lower panels. So what can we see? What is the idea behind this mechanism? So initially the trajectories are in this chaotic layer involving the resonance island, or in the separatrix of this resonance. So as you can see that the black dots are the initial conditions, and the remaining is the phase space. Okay, this is a point array section. So the initial conditions are you can see in the separatrix of the resonance, and when the amplitude increases, the trajectories spread over the resonance, occupying the whole. They come through this chaotic layer. Okay, and you can see that they cover all the resonance island, and then when the field is turned off, part of the trajectories are in a higher energy. This is a way of controlling the transition between two energies. Not all the trajectories are driven towards the higher energy, but this result can be improved if you chirped also the laser. You can drive more trajectories to higher energies, for instance. And they have performed such calculation, and these authors argue that they can explain about this mechanism. Experiments between the excitation of Hilbert atoms by microwave fields, for instance. Okay? There is also a quantum explanation, but there is a classical interpretation of these results. Okay, so this is historical. So what is our alternative to do the transitions? Our alternative is to perform a transition by means of invariant tori, or invariant tori. Okay. Yeah, we know from the KAM theorem that some invariant tori persist in the present of the perturbation. Yeah. Usually when we are dealing, at least in this model, with lower frequency, the deformation of this invariant tori is quite small. But we have seen, I will show some results in the next slides, that when we raise the frequency, the amplitude, this tori has a quite impressive deformation, impressive bending. So I will show in a moment. So our idea is the same. We have original Hamiltonian H0 and a coupling with the external field, H1. Okay? And in the present of H1, we are assuming there are still some invariant tori. Okay? And we can quantify this deformation in angular variable, in action variable by this J is the action variable. J is J plus this delta. This delta is the, oh, thank you. This delta is the, we call the deformation of the tori, which depends on the parameters of the laser pulse and also depends on the coupling, okay? And we want to make the transition in this invariant tori using a field like this. We have this coupling, which is quite general for a dipole coupling. And we have a field that's E of t. Here we have usually an envelope function and an harmonic field. Okay? Here, for simplicity, I will talk about only this square envelope. Okay? But we can use like Gaussian and other kind of envelopes. So we have some couple of years ago seen what we call this energy cubes. They always start, this idea always starts with that. These energy cubes, it's like we have here the phase space like the x and the p, the space and moment here. This is in fact taken as it's a kind of extended stroboscopic map here. Okay. And here the energy. The energy, you can think about the energy of the unperturbed Hamiltonian, the H0, the value of H0, of the value of, in this particular case, the value of the Hamiltonian in that surface of section. Okay? And here the field is turned off. That's why you can see the here the projection. It's like the same figure I have shown you before. This projection here in XP, and you can see that plugging here with this X is the energy. You can see the curves corresponding to each one of these stories. Okay. So when we turn on the laser field, we could see an interesting thing. When we turn on the field, we can clearly see that the bending of these tori here. Okay, some resonance island appear, a chaotic sea appear, but we have focused on that bending of the torus. And we have searched many parameters of the systems, and we have found that comparing low frequency with high frequency, we noted that, well, in low frequency, nothing very interesting happened because the bending of the tori was quite small. But when we use very high frequency and also high amplitude, we could see that regularization of the phase space, and also that the surviving torus has a significant band. Okay, we call this range in energy is the inclination. Okay, so I have 5 minutes. Yes, one. Okay, so I will go direct to the point. So I have to jump some of the results, but this is it's the main idea I can tell you. Well, the idea is the following. So when we have a bending torus, so we can use this bending torus to make the transition. Okay? So if initially a trajectory, for instance, is here in the lower part of the torus, we turn on the laser, the trajectory will move on that torus, and if you turn off the laser here, the field here, it will gain energy and will afterwards be in the higher energy level. So that's the main idea, and this can be used also to control dissociation. These are also surviving torus that cross the separatrix concerning the dissociation of the Morse potential. Okay. We have tested for several trajectories. We can do, for instance, photoassociation. The particle come here, and we turn on the laser field, and after the field is turned off, we trap the trajectories inside the well. And this also works not for one single trajectory, but for an ensemble of trajectories. So, my conclusions. We can use this surviving torus to make non-chaotic classical transitions if you design correctly the laser fields, and intense and high frequency field can be used to perform this, to have this torus with large deformations. And we are still pursuing this conclusion here that a combination of several pools of lower energy or lower frequency also may be used. But we have always to be off resonance. This is the question here, which is easier for high energy, higher frequency. And we have also seen that perturbation theory can give a good insight on that calculation. Thank you.
Thank you very much. So while the next one is coming down to set up his presentation, we have time for a brief question. So you're adding this perturbation to get sort of these tori that reach all the way up. How do you design that perturbation?
First, we have initial energy. Suppose you want to reach higher energy. So we first search in the parameters of the laser those parameters that form a torus that link both energy. And then we have just to set up the timing of the pulse. Which relatively easy, can be done directly by numerical calculation or by means of perturbation theory.
So what you modify is what, the shape of the pulse, or do you have an extra field that gives you this perturbation?
Pardon?
You said you were adding a perturbation to your initial Hamiltonian. You took the Morse, you took the electric field, and something else.
No. It's the Morse and a external perturbation that is turning on and off afterwards.
Right. Okay. Thank you very much. Another Bruno is giving the next presentation.
I think this is yours.
So, Bruno Boaretto. Microphone someplace. All right.
All right.
And we'll hear about networks of the Hodgkin-Huxley type. All yours. Thank you.
Good morning to everyone. Good morning to everyone. My name is Bruno Boaretto. I'm doing my PhD in Universidade Federal do Paraná. My advisor is Professor Sergio Roberto Lopes, which is in the same group of Professor Viana. And today I will present this work, which calls Protocol for Suppression of Phase Synchronization in Hodgkin-Huxley-type networks. This is the outline of my presentation. First, I will quickly talk about the aim of this work. After that, I will show the neural models that we use in this work and his dynamics and how we quantify phase synchronization in our neural network, followed by the results and the conclusions. So in my master's dissertation, I used to work with several methods to suppress the phase synchronization of a neural network. And one of the method which proves to be more efficient is when we apply an external pulsed current in the network. So the aim of this work here is to study an optimized protocol of this suppression by the application of the external pulsed current. So now I will show the neural model that we use and how we measure phase synchronization in the neural network. In this work, we use an adaptation of the Hodgkin-Huxley model proposed by Brown et al. Sometimes we call this model the Hubbard-Brown model. I know Ulrika has a great contribution in this model. And basically, this model consists in the evolution of the memory potential of each neuron as a function of 6 ionic currents. The first and the second current takes into account the sodium and the potassium ions. The ISD and ISR are slow currents, is part of this adaptation here. The leakage current takes the contribution of the non-gated channels. And the coupling current takes into account all the other neurons in the network. So each neuron of the network has one equation like this. And the coupling between the neurons is given by this equation here, which depends on a coupling parameter, epsilon, which controls the coupling strength. And we will study how the synchronization varies as a function of this parameter. We have a normalization here. Eij is the element of the connection matrix. It tells us who is connected to who. And R is a dynamical variable which represents a chemical coupling. So this is an example of the dynamics of one neuron of the network. So is the memory potential, is the evolution in time of the memory potential of the neuron, as a function of time, of course. And we can observe that the neuron depicts a set of spikes followed by a rest in time. And this behavior we call bursting behavior. So we can associate the memory potential of each neuron with a geometric phase. When we impose that every time that a burst starts, like here, here, and here, the phase is 2 pi multiple using this interpolation here. So here we have in the red line is the cosine of his phase. So every time that a burst starts, the phase is 2 pi multiple, then his cosine is equal to 1. So making this association, each neuron of the network, it will be corresponds to a phase. It will be only one phase. And we make this association, we can measure phase synchronization in our neural network by using the Kuramoto order parameter. So when R is almost 1, when the modulus of the Kuramoto's order parameter is almost 1, we say that the network is synchronized. When it's almost 0, we say that the network is unsynchronized. And we also define the mean order parameter, which is the average of the modulus of the order parameter in time. Now I will show the results of this work. In this work, we simulate a neural network with 5,000 neurons. They are coupling in a small world topology of connection. And first, we will analyze how the synchronization varies as a function of the coupling parameter. After that, we will verify how the synchronization is affected by the application of an external pulsed current. And After that, we will optimize and quantify how much current we need to apply in our neural network to suppress the synchronization. Here we have a synchronization result, is the mean order parameter as a function of the coupling parameter for that neural network. And here for a higher coupling parameter, the network synchronizes because R is almost 1. So this is completely expected because as we increase the coupling between the neurons, we expect that they start to synchronize with each other. But in this lower coupling region here, the network presents a local maximum of synchronization. And as we increase the coupling between the neurons, the synchronization decrease a lot. And this characterizes a non-monotonic evolution of the synchronization as a function of the coupling parameter. So what we want is to apply some kind of perturbation in our network to suppress this local maximum of synchronization here. And we do that perturbation, that disturbance in the network by the application of an external pulsed current. The current that we apply in the main equation of the neuron, in all the neurons in the network, is described by this equation here, which is a little complicated, but is just basically the Fourier representation of a pulsed current with period tau and amplitude C0, and a width of each pulse is given by tau1. So in the time of activation of the current in each period is equal to tau1. So here we have another synchronization result, is again the mean order parameter as a function of the coupling parameter for different values of the amplitude of the current. So the black dashed line here is the previous case when we don't have any current applied, so this local maximum is still here. When we increase a little bit the amplitude of this current equal to 0.05, the dark gray line, the local maximum still exists. I know in that case the synchronization decreases a little, but we are able to see this local maximum here. And the solid curves here, the another 5 cases equal to 0.1, 2, 3, 4, and 5, the network depicts a monotonic evolution of the synchronization. So the local maximum completely gone. And this monotonic evolution of the synchronization is more frequently seen in another chaotic oscillators. For an example, the Kuramoto's oscillators. So for lower coupling parameter, we have the synchronization. When the coupling reaches a critical value, the network is synchronized. And but for some cases, for an example, the cyan line here for 0.5, the network, the amplitude is higher in that sense because we start to change the higher coupling region here. So in that sense, the current equal to 0.1, the amplitude equal to 0.1 is more efficient because suppress the unexpected synchronization here, this local maximum of the synchronization, but does not affect these regions for higher coupling parameter. And what we want to know now is what's happened in time from this point to this point. So how long does it take to the network desynchronize it from this local maximum of the synchronization to the desynchronization case? So to do that, we need to fix the coupling parameter. We fix here in this local maximum equal to 0.01. And we will study how the synchronization varies in time. Here, so in the first 200 seconds of simulation, we just don't apply any external input. So the network synchronizes because of that local maximum of synchronization. And after 200 seconds, we turn on the current. So we make this for 5 different ratios of tau on tau. For example, tau on tau equal to 0.1, 2, 3, 4, and 5. And we can observe that for a lower ratio of tau and tau, the current is not strong enough to suppress the synchronization. And the other 4 cases, the synchronization is suppressed really fast. And higher is the ratio of tau on tau, which is the width of the pulse, faster is the desynchronization. And after 400 seconds of simulation, we turned off the input. So we can observe that in all these cases, the network recovered the synchronization symptom. And in order to study some kind of multi-stability, we repeat this procedure of turning on and off the input in the network several times. So in each 200 seconds, I'll change the input on to off, on, off. And every time that we turn it off the inputs in the network recovers the synchronization symptoms, which is that local maximum of the synchronization. So to keep the network suppressed, to keep the synchronization suppressed, to maintain the network in the desynchronized state, we need to turn it on, keep the current turned on during all the time. And so we studied, we made a protocol of changing the amplitude of the current after the network desynchronizes. So what we want to know now is how much current we need to maintain the network in the desynchronized state. So again, in the first 200 seconds of simulation, we do not apply any external pulsed current. After 200 seconds, we apply an external pulsed current equal to 0.1 to decrease the synchronization, to suppress the synchronization. And after the 400 seconds, we change the amplitude of the current. So we do this to study how much current we need to keep the network in the desynchronized state. And each panel here corresponds to a ratio of tau on tau, 0.2, 3, 4, and 5. And in each curve in these panels corresponds to a new amplitude that I namely C0 after. So in the first panel of the ratio tau on tau, none of these cases are able to keep the network desynchronized. And in the second panel, when the current is equal to 0.05, the network, we keep the network in the desynchronized state. In the third panel, 0.4, for a current30 than 0.04. And the last panel here is for current higher than 0.03, which is 30% of the initial current here. In order to study how much current we need to apply, we define this quantity with a method called J, which computes the current density flow in a time interval of 1 hour. And here in the science, we made this study of this quantity equal to, as a function of tau on tau, and C0 after, which is that new current. And the gray area is when the network, we fails in the suppression of the synchronization because the network recovered the synchronized states. And the other case is when we are able to suppress the synchronization. And this threshold of cyan lines is the optimized cases. So now my final considerations. So we studied the effect of the application of an external pulsed current in our neural network. When the amplitude of this current is higher than 0.1, we are able to suppress the phase synchronization of the network. To keep the network desynchronized, we need to maintain the current turned on. Otherwise, the network will recover the synchronization. And after the suppression, the amplitude of the current can be reduced to maintain the network in the desynchronized. In some cases, in 70%. We published these results in Physica A. And I would like to thank all of you for the attention, people of the organization, the co-authors, and of course, for the financial support. Thank you.
Thank you very much. We have time for questions. Ulrike.
So when you apply, so to say, the coupling first, then the dynamics changes usually in this kind of models to something chaotic. It's not bursting anymore, so not periodically bursting. So probably chaotic bursting, something like this, when you have it in the network. And what happens to the dynamics when you have your periodic signal? Because this could bring you back, so to say, to a periodic dynamics. So how would the dynamics in the system change when you apply your
Yeah, it's like the external current takes do the job of the coupling current for a higher coupling. Does that answer your question? Maybe?
Not really. So what is the dynamics? So if you would now
When,
look just
all right.
at
If I-
your
if I-
quantity, which is basically a mean quantity. So if you look at the dynamics of your system, so what is
it's chaotic.
the factor in the network?
It's chaotic. When I apply,
Even with the periodic pulsing.
yeah. But the bursts are periodic, shows some periodic behaviors, the bursts of the neurons. And when we apply the coupling, the current, the bursts start to be more chaotic. We increase chaoticity in the bursts, periodic bursts.
Okay. So will the next one please come down and set up, and then you can ask your question.
So, a very simple question. So the polarizing current, when you apply the polarizing current to a single neuron, the spikes tend to disappear. I mean, the action potential tend to disappear. In an experimental setup, you apply any depolarizing current, and the properties of the neuron in the action potential tend to disappear. And my question is related to the previous one, in the sense that once we apply this depolarizing current to the whole network, how the spikes inside the burst are modified. Because your synchronization is modified by the synchronization of the global network. But if you look into more, the details of the dynamics, you are probably you are simply disappearing all the spikes, which of course in the sense of neuron transmission information has no meaning because you are not communicating anymore.
Yeah, but in our simulations, the local dynamics is preserved. We don't change it a lot, just a little bit in the period of in the interburst interval. But we are we take this care of keep the bursting behavior.
Okay.
Thank you. All right. Is that for you?
Thank you very much.
This belongs to you.
We need the tracker for the camera and the microphone. Okay.
Hello, can you hear me?
And we'll continue with networks by Kalel Rossi. All yours.
So hello, everyone. I'm Kalel. I'm in the same group as Bruno, who's just presented. We are both have the same advisor, Sergio Lopes, and are in the group of Professor Viana. We both study the same network, which is a network with bursting dynamics. But we have different perspectives on the analysis of the network. I will study the effect of the variability between neurons, that is, how the interburst intervals are chosen, how the neurons choose their interburst intervals, how the interval of interburst intervals, how large is the dispersion of the quasi-periods of the neurons. The interbursts are not the same. They are chosen according to some rule. And the changes of this interval of interburst intervals affects the phase synchronization of the network. So first I'll give you an introduction to the network, a brief reminder of what Bruno has just presented. Then I will jump right onto the results. So the neurodynamics are the dynamics of the brown neurons, which are bursting neurons. And the neurons are identical. That is, the parameters we use for them are the same. The coupling is chemical and excitatory only for this case. And the connection scheme is random. So the model Bruno has just presented follows these equations, these main equations. And the most interesting value is the membrane potential of the neuron. You see here the chemical coupling. And this parameter is chosen such that the synapses are excitatory. This is the potential of a neuron, a single neuron. So you see bursting behavior. This, we are interested in the times at which the neurons start bursting. This is the most important time for the neurons. And the time between two successive bursts, we will call, I just called, interburst intervals. So the topology is random, follows the Erdős-Rényi algorithm. We use 1,000 neurons and about 5,000 connections. The first phenomenon we're interested in is phase synchronization. As you all know, phase synchronization will happen when neurons start their burstings or their spikes, depends on which case, at the same time. And phase synchronization has been associated with various healthy behaviors and various unhealthy behaviors. So it's a quite ubiquitous phenomenon in biological networks. To measure phase synchronization, we use the Kuramoto order parameter. As you all know, it's a quantity that goes from 0 to 1. And the larger this quantity, the more phase synchronized the network is. That is, if R is 1, the maximum value, all neurons start their burstings at the same time, exactly the same time. The other phenomenon I'm interested in is variability. I just said it's when it's the size, it's the dispersion of the interburst or interspike, depends on which case, intervals. This variability is quite important in biological networks because it can affect the information processing capacity of the network. To quantify variability, I use this coefficient of variability, which is the standard deviation of the interburst intervals, divided by the mean, the average of the interburst intervals. This standard deviation can be calculated in 3 different ways. The first one, the simplest one, is this third one, in which I take all the interburst intervals of every neuron, flatten them out in a list, and calculate the standard deviation. Another way would be to calculate the standard deviation of the interburst intervals of each single neuron and then average, or calculate the standard deviation of the interburst intervals of different neurons and then average across time. 3 different ways, they give almost the same results, as I will show now. These are 3 different quantifiers over the coupling strength, epsilon. The first, each column depicts a different temperature value. So for this first temperature, 37 degrees, the Kuramoto, the mean Kuramoto order parameter is this one. It's what you would expect if you study Kuramoto oscillators, this monotonic increase of the synchronization. But if we increase the temperature, we start to see different behavior. We see this first maximum, this local maximum, which Bruno studied. If we increase the temperature even more, for 39 degrees, we see the network synchronizes very fast for very low coupling strengths. This synchronization here and here is quite large. Even the spikes in the bursts are synchronized. This is almost not, it's not, but it's almost complete synchronization for small coupling values. So you see that changing just this parameter, the initial conditions, the topology is the same. Just changing the temperature, the network behaves quite differently. Where does this come from? So what I do is study the variability between the neurons, calculated in those 3 different ways I just talked about. And you see that, for example, for 38 degrees, when the network starts synchronizing, the variability between neurons starts decreasing. And when it starts desynchronizing, the variability goes up. For 39, for example, when the synchronization is very high, the variability is very low for these 2 cases. Then for 37, you can see easily that it doesn't have a local maximum because the variability, or because it doesn't have the local maximum, and the variability is very high. So you have this correlation between degree of synchronization and the value of this variability. For higher coupling, the correlation is not exactly, it's not so clear, because the coupling is so high that it changes the dynamics of the network. But the most important thing I'm talking about here is for these low, small values of coupling. In these cases, the variability correlates very well with the degree of synchronization. I will now show to you an animation of the burstings of the neurons for these two temperatures, 38 and 40, for these two values of epsilon, for the local maximum and the global maximum. This is for the local maximum. And for the global maximum. So you see in the two cases, the neurons burst at around the same time. But the dispersion is lower in this case. In the previous, the local maximum, there are quite a few outliers. You can see this more clearly in the raster plot. In this, I plot in the y-axis the index of the neurons, and in the x-axis the time. A dot here is, I put a dot here when a neuron bursts, a neuron of a certain index bursts at a given time. So you see the clustering of the network. And the coloring scheme here is the following. I take this vertical line, which I call a bursting event. I take the times at which the neuron started bursting, all these n times, calculate the mean, calculate the standard deviation. And then I collect all the neurons that started bursting within one standard deviation of the mean and put them in a cluster. This is how I define a cluster here. Those in the cluster I color blue. Those not in the cluster I color red in the first case. And in subsequent times, I keep this coloring scheme. So a neuron that is blue here or here or here or here is a neuron that was in the cluster in the first time. A neuron that is red here is a neuron that was not in the cluster for the first time. So you see, in this case, neurons that are in the first cluster remain in the cluster for subsequent times. In this case, neurons that are in the cluster for the first time don't necessarily remain in the cluster for subsequent times. Or conversely, neurons that are not in the cluster in the first time go in the cluster for subsequent times. So in this case, you have this mingling of neurons. Neurons sometimes are in this main cluster, sometimes they are not. In this case, neurons that are in the cluster generally remain in the cluster. Another way to say this is that neurons here are more loyal to each other. If two neurons are in phase, they tend to remain in phase for subsequent times. Here, neurons are not so loyal. If they are in phase for some time, they may not be in phase for subsequent times. This we call promiscuity. Neurons are promiscuous in this way. They tend to mingle. This is for 48 degrees. And you notice here that the promiscuity is low. So neurons are not, promiscuity is low. Neurons are loyal. Here, promiscuity is high. Neurons are not so loyal. And this is, you remember, is when the variability was low. This is when the variability was high. So again, you have this correlation between low variability and low promiscuity, high variability, high promiscuity. So correlation between variability and promiscuity for 38 degrees. For 40, I have this animation as well. This is in the case where there is spike synchronization. So the neurons are more tightly synchronized, more together. And they tend to stay in two clusters. One that starts bursting, and then another. This is clear in the raster plot. For 40 degrees, region with spike synchronization. So you see they cluster around, go around the cluster. And in this case, neurons that are in the first cluster remain on the cluster for all times. Very low promiscuity, very high loyalty to the cluster. For very low coupling values, strength of the coupling. For high coupling, neurons are not loyal once again, so same behavior as before. This has very low variability and very low promiscuity as well. So correlation between variability and promiscuity. I can define a cluster algorithm to quantify these results which I just introduced in a visual way. But the main idea is what I just said. Take the times, calculate the mean, the standard deviation, and collect the neurons which are within the standard deviation of the mean. So quantifying that behavior, we get what we just saw. For 37 degrees, the increase of this is the size of the cluster, normalized by the size of the network. And these blue dots are the number of neurons averaged over time that stay in the cluster. And this axis here are the number of neurons that don't stay in the cluster from one time to another, averaged over time. So you see that there is this monotonic increase in the size of the cluster. But the normalized number of neurons that stay in the cluster here is about 80%, let's say. So from one time to another, about 80% of the neurons stay in the cluster. Only. From one time to another, 20% of the neurons leave the cluster, even with high forcing, even with high synchronization. So you remember that this was like a chromotor parameter of the order of 0.9, 0.95. And even for this case, neurons don't stay so much together in the cluster. This is for 38 degrees. You notice the interesting thing here is that the neurons are much more loyal to each other just in the peak of the local maximum. So this is just a quantification of what I just had just argued about, that promiscuity is correlated with variability. The neurons are more loyal to each other when the coupling is low. Same for 39. In red, I plot the second cluster, the neurons that are not in the first cluster. And you notice for these two cases that the promiscuity is very low when the variability is low as well. This is another way to see what I just said. If we build the cluster by not just asking the neurons to stay together for one time, but asking them to stay together for n times, you see this behavior. So for the local maximum, there are about 600 neurons that stay together always for 50, stay together for at least 15 times. For the global maximum, the asymptotic case, almost no neurons stay together for 15 times. So once again, they go out of the cluster. Some neurons go out of the cluster, some neurons go in the cluster. And this happens in such a way that the mean value of the cluster doesn't change much. This is the standard deviation over time. So the mean value of the mean size of the cluster doesn't change much, but because the number of neurons that stay in the cluster and that leave the cluster and that enter the cluster is more or less the same. So this is for 40 degrees. You see that neurons stay together always. Very low variability, almost zero. And here, with high forcing, neurons don't stay together. So I showed you here the correlation between variability and promiscuity. It's a relation. What I'd like to argue now is that it's kind of a causal relation in the sense that if there is variability, then there will be promiscuity. Variability leads to promiscuity. Why? Variability measures the size of the interburst interval that the neurons can choose from. You can imagine there is a pool of interburst intervals a neuron can choose. And the bigger this pool, the higher the chance that two neurons that start firing at the same time for one time will not fire again together in the next time, because they will choose different interburst intervals, and so will burst again at different times. So variability leads to promiscuity. To summarize my results, I have shown that variability is inversely proportional to the degree of synchronization of the network, especially for low, small coupling strengths. And that variability leads to promiscuity. And this I believe to be, though I have not shown, because this promiscuity variability is a statistical process, this should be general. That is, given that you have variability in your network, you could expect that there will be at least a degree of promiscuity. So I'd like to thank you all for your attention. Thank you for my collaborators. And that's it.
Thank you very much. We have time for questions. Yeah.
I don't know your field very well, but when you were talking of clusters and some elements come, some neurons coming in and out, how are you clearing that from your network?
What do you mean? Some neurons go in and out of the cluster, yes?
Yes.
I don't understand the question.
Finding that out.
So for each time, I calculate the cluster. I know which neurons are in the cluster. And then I see which neurons that are, for example, in this cluster for the second time are not in this cluster for the first time. So I know that, better example, I know which neurons are in this first cluster. I know which neurons are in the second cluster, okay? I see which neurons were in the cluster and which, but are not in the second cluster. These neurons left the cluster.
How do you figure that out?
No, not for here, from here. I have a code that does that.
Okay.
So this is what I meant by I define an algorithm, and the algorithm figures out. I don't do this visually, no.
Thank you.
Okay. Any more urgent questions? Well, while the next one is coming down and setting up. No more questions. So thank you very much.
Tá ligado? Deixa aqui.
Aqui?
É, você aqui. Pode pôr aqui. Opa. Ok, entendi. Working. Okay.
Something does happen. All right, good. So we come to the last presentation before lunch. André Gusso, who will tell us about robust chaos induced by two frequency excitations.
Hi, Carl. Thank you. Hi, everybody. Thank you for your audience. I'd like to thank the organizers for the chance to present this work here. So what I'm going to do here is to present you some already published and some not published results, therefore some new results, regarding the emergence that we have observed of we identify as robust chaos in some physical systems. In particular, we have results for micro and nano resonators and for the well-known Duffin oscillator. Now, this work has been done in collaboration with my colleagues from the Exact Science Department of the Fluminense Federal University, Boaretto Gomes Dantas, who is here in the audience, and he's also presenting a related work as a poster. It's hanging there. And my colleague Sebastian Jujevic is also collaborating. And we have also the great collaboration of Professor Viana from the Federal University of Paraná, which has this great experience with chaotic systems that we have been studying here. I'm going to start presenting results for micro and nanoresonators. You may not be familiar with such devices, so let me introduce you to these devices. So we have some pictures of devices. They exist in real world. Okay, it's not just a theoretical work. They are relevant systems that are widely investigated experimentally and both theoretically. We have examples of the kind of system that we consider here. There are many configurations of what are known as micro nanoresonators. We investigate here this kind of resonator. It's comprised of a beam. It's a suspended beam, okay? And in this particular case, the beams are clamped at both ends. We have therefore forming a bridge. But we also have some variations in the case they are clamped only at one end. Then we have a, oops, the problem with the finger, a cantilever. But consider the case when they are clamped at both ends. We have here the case when they are actuated by one-sided electrode. We have here an electrode below the resonator. So when you apply a voltage here, the system can be displaced. It's a time-varying voltage. You have a system, it can vibrate, so you can make it resonate, for instance. That's how you make the system to work. And this is the case of system that we study here, which is a beam clamped at both ends, but actuated by two electrodes. We have an electrode on this side and this side too. Here you have an amplification. You can see the beam here. There is a gap, so you have an electrostatic actuation of such systems. Okay. What are the reasons why these systems are investigated so much? They are indeed investigated a lot. Well, they have many potential practical advantage compared to other kind of electronic circuits. And we can see here an image of a microchip. We have the resonators, two resonators here. They are very small. They occupy a very small area compared with the rest of electronic circuit that use it to excitate system and perform the readout of the vibrations. So they are very small. So this is one advantage that they are small. They occupy a small size on a die. And as a consequence of their smallness, they usually have a low power consumption, which is also quite interesting for applications in mobile devices. So you can save your battery. And another interesting characteristic is that as they are small, they can attain high frequencies of vibration. This is important for telecommunications where you have frequencies of the order of hundreds of megahertz and gigahertz, and you can get such frequencies with the smallest devices. Not that easy, but hundreds of megahertz you can get. Okay? They have been investigated for many potential applications. There is one application that's already available. You can buy chips with resonators of this kind for a specific application. But they are investigated for applications such as electronic signal filters. Now you have the bandwidth, that resonance curve. Usually the systems have very high quality factors, so you can get a very narrow bandwidth. So you can filter signals with great fidelity. Because of these high quality factors, you can make them work very well as reference frequency oscillators, as clocks. You know, your computer has a clock of 3.4 gigahertz. So you need a reference oscillator to maintain that frequency. And they can be used as reference oscillators. Okay? They are also investigated for small mass and chemical sensors. I don't know the latest results, but last time I saw it, they could measure the mass. They could sense the mass of small macromolecules. You know, the idea is to measure small molecules using these devices. And how they do that? Well, they set the system to vibrate in the resonant frequency. So when you add a mass, the resonant frequency changes. So you can measure this change and say, okay, I have a mass that was coupled to the system. That's how you can also measure the presence of chemicals. Well, this all has been investigated in the linear regime of the system, so with small amplitudes of oscillation. But it's hard to avoid in such small systems to get into a nonlinear regime. So people have been exploring those systems in their nonlinear regime. You can have some interesting results. You can make them work as reference frequency oscillators with better frequency stability, using some tricky results to nonlinear couplings of modes. Okay, and there are a few other results, but we are interested here. This has been an idea that has been put forward quite recently in the literature. We can use these devices as sources of chaotic signals. They could generate chaotic signals for use in secure communications as random number generation. We have been investigating this. The poster we have there that my colleague is presenting is exactly about the use of such devices for random number generation. You can use them as sources of continuous time chaotic signals for radars, for instance. There are many possible applications of chaotic signals, and they can be used as sources of chaotic signals. Well, we have a theoretical model for this system. This is schematics of our device. This is the beam. It's clamped at both ends. Here we have the electrodes. They are a separation between the beam and the electrodes. Here is D1 and D2. We're going to make them the same in our analysis. You can apply different voltage here. You're going to use this fact. And when you apply the voltage, the system is displaced here. Okay. We have this variable I'm going to mention soon. This is W. Is the displacement of the beam. And here in particular, we have here the displacement at the middle of the beam, which I call Y. It's going to be a function of time. More details on the model. I'm going to present just a few aspects of the modeling, okay, theoretical model of the system. But more details can be found in these works that we have done. Okay. So we start with this partial differential equation, which is nonlinear. Here is the this is essentially the beam equation, the Euler-Bernoulli beam equation. Here we have the spatial derivatives, which are indicated by the primes here, time derivatives by the dots. Okay. We introduce here what we call a linear damping to contrast between now we know as nonlinear damping. Nonlinear damping can be important for these systems, but it's very hard to model. I've been working on this. I have proposed nonlinear damping mechanisms for this kind of devices. But well, we're going to just consider viscous damping here. This term is the beam stretching term, which results in a nonlinear behavior of the beam. It's a nonlinear restoring force. It adds a restoring force to the one coming from the elastic properties of the beam. And here we have the contribution of the electrostatic force. Okay. Well, we do not solve this partial differential equation. What we do is simplify the model using the Galecki method. So reduce the model from this partial differential equation to a nonlinear ordinary differential equation. I consider that our system, as is usually done in the practical devices, they operate the system at frequencies that are below or close to the first resonant mode. So basically, the vibrational mode has this form here. This is the form of the function phi 1 of x, which I mentioned here. So I assume that the system is vibrating with this mode shape. So I have to find we get a ordinary differential equation for the variable u here. But instead of work with u, we work initially with y, which is the displacement of the middle of the beam here, the largest displacement. And you get this equation. This is basically the harmonic oscillator with a cubic nonlinear term. And we have also this electrostatic contribution here. It has this complex form. But we do not solve the problem using this variable y. We simplify further the problem with an adequate chain of variables. And we work with this equation here. Okay? It's harmonic oscillator. We have only two the interesting chain of variables that we perform here. The details are in the work. We have only parameter beta here, which is related to dissipation, and alpha, that's given by this simple expression here, which is the strength of the cubic term. Okay? But you have this term here, which has this form. And depending on what apply the voltages, V1 and V2, in fact, this term, it sums up to this one and this one, so it can change the effective linear and nonlinear coefficient of the equation. And you have other terms that contribute with other nonlinearities. S here is basically defined by the maximum displacement over the gap. And it's going to vary between -1 and 1. -1 means that you have heated one of the electrodes, +1 the other electrode. Okay? It can vibrate only between the electrodes. We solve this equation. we have these integrals here. We solve the problem. We do not solve those integrals. We do this approximation here. So with that, we get some results. But we want to model our system. We solve this equation here. But we want to simulate a realistic system. So we have chosen a system with these properties, a nanoresonator. Well, the results also work for a microresonator. We consider a nanoresonator because nano stuff is fancy. Everybody likes nano stuff. So we consider a nanoresonator, a length of 5 micrometers with this width and thickness, okay, very thin. Symmetric gaps, that means gamma here is equal to 1. And you consider that we are applying 2 different voltages, and we have the possibility to have 2 alternate currents being applied at each electrode. What people have been considering so far is just that you skip this term, and what people do is to excite with only one frequency. But we are adding here the effect of this second frequency. So we have here the parameter zeta, which is the normalized frequency. We have here tau, which is the normalized time, and the important parameter here is the frequency ratio R. Okay? So we're going to vary these parameters here to investigate what we get for our system. So it's important to note that our system depends on the values of the applied bias voltage, which is the DC voltage, and also depend on the VDC. We get different potentials as we vary VDC. For a smaller VDC, you get a potential which is in this inner region here. We get only one minimum, the single L potential. But as we increase the DC voltage, we get a 2L potential. Okay? So we have chaos in both configurations here, but here we have the usual well crossing that you see in the system, and in fact the dynamics in this case is richer. Okay? Well, during simulations we have done a lot of different stuff, vary the many variables we have here. And what we observed in numerical simulations is that when the dissipation is sufficiently small, I'm going to talk more about that, the frequency excitation results in a huge increase in the area in parameter space. This parameter space here, VC, VDC, and zeta, is the frequency, where chaos occurs. So what have we seen? These are some of the results. Here I have results. This panel here is the case when I have only one frequency of excitation. We have presented detailed analysis of this system in this work in which we consider only the case of excitation by one frequency. Now, this has been overseen in the literature, decided to study this in more details. So this is a phase diagram which shows the regions where you have periodic behavior here with period 1 in yellow, period 2 in green, period 3 in orange. We have other periods here, period 4 in blue, etc. Here, the black regions are the ones with chaos, positive Lyapunov exponent. And this region here is the one that corresponds to pooling, that phenomenon. The system can sort of escape to infinity. Our system can suffer this escape for infinity. But in fact, it escapes to the electrodes, not to infinity. So it hits electrodes. It's going to be shown here in purple and red in the next panels. So we have presented more detailed analysis of this case to only one frequency. This work have analyzed the basins of attraction, which are quite interesting in this case. You can have mood stability, as it's more or less evident from here, because here we consider only one initial condition. So what if you vary, you're going to vary a little bit. And you calculated the fractal dimension of such basins using the usual methods, box counting, and the calculation of the uncertainty exponent. But you also use a new method based on the calculation of the basin entropy. So you can now calculate the fractal dimension another way too. Well, when excited system at second frequency, we're going to start with a smaller frequency here, smaller amplitude, on 0.2 of the initially applied voltage. You already get a huge increase in the area with chaos here. Okay. It's interesting to note here that now we have period 1 here, period 1 and 2 mostly. But period 1 in this case, as the system is excited by 2 frequencies, it has to phase in with these 2 frequencies. And the system is periodic in the end. The excitation is periodic. But the period, in the case of R equal 1.07, the period is this one. It's 107 times the period we had here. Okay, so the analysis here takes much more time. You have to consider much longer periods to make the analysis. Well, as you increase the voltage, you have an enlargement of the area with chaos. And finally, you get this when the voltages are the same. Okay? We can vary some parameters here, like zeta, the frequency. R and beta, and you get similar results. I'll show you here that you get similar results. This is a case where zeta is now 0.4. One frequency, you have only a small region with chaos, so you want to use the system as a source of chaotic signal. This is not the ideal situation, but you can increase this up to this. Okay? So you not only have a large region with chaos, but also the basins of attraction are quite robust in the sense that you don't have other attractors here. You can calculate for many points here. This is the basin attractor. All the points here goes to a chaotic attractor. Okay? Just to convince you a bit more that we have chaos here, this is the work we have published, I'm going to mention soon. These are the point correct sections are actually what we call double point correct sections because you have two exciting frequencies. So you have it sample the system. In the case of R, you call 1.7 at every 107 times the basic period that you have of excitation. So it takes much longer to calculate these attractors. What point is that? Well, okay, we have got a very large region in which we have chaos. This is nice if you want to use our system for practical applications because what problem you want to avoid? Whenever you produce a device, and it's even more problematic when you have a nanoresonator, you have fabrication tolerance. So you aim at having a system with a given dimension, therefore a given frequency, but it's not going to be exactly that what you're going to get. So you got to have a tolerance about the region that you're going to have your device working, okay? So it's important to ask yourself if you really have in this region, if you have no windows with periodicity, and particularly if the chaotic attractor is unique. Because for practical applications, you want a system with given chaotic dynamics. For instance, your chaotic dynamics implies in a given frequency spectrum that you want to use, or it generates random numbers in a given way. So if having chaos is not enough for the applications, you want to have the same attractor. So we investigated this, and basically answering these questions is the same as answer this question here. Is there robust chaos in the system when excited by two frequencies? Well, this concept is not widely known. The concept of robust chaos was introduced in this work by Banerjee, York, and Grebogi. So they state the following. Chaos is robust when the chaotic attractor persists under a change in the system parameters. Okay? So the idea of chaos is the one when you vary the parameters, and the attractor is exactly the same. You can see that in their example here with a map, the circuit results in a map. You don't have exactly the same attractor as vary the parameters. But you don't have periodic windows. That's good. Okay? Maybe good enough or not. That all depends on the application that you're going to do. But it's already good. But ideal chaos is the case when you have always same attractor. But you're going to accept here that our chaotic attractor may vary a little bit. You're going to see that's what happens in our case. So, 2 minutes, OK. The robust chaos is really required in practical application, rely upon physical systems. You have maps, but we have very few systems which are continuous time systems that have been investigated. Well, we have I'm going to present some results representing this work. Oh, sorry. So we have this region here, which the region we have found that we could have robust chaos, but we decided to investigate with more details this region here. It seems small, but it's already it's big enough, this region, okay? We consider a total of 5,000 points within this region and vary R and beta, and so what happened? What we get is the following. When you vary R, you see that except for a few frequency ratios, you get a very small fraction of points that are not chaotic. So in this region, you have all points in that volume, 5,000 points, they have chaos. Okay. So basically, what we conclude that we have avoided frequency rates of this like this, made up of small integers. And in fact, all the ratios here can be represented as rational numbers, but we have only avoided some frequencies here, and you can get good results. You can control frequency easily, so this is not a problem. And as we vary beta, you can see that we have to avoid large dissipations. For small dissipations here, so essentially small dissipation, you don't get any points here that have that are periodic, for instance, or pull-in. But is this attractor that we have, is it robust? So I investigated if our attractor is robust. Basically what you do is we tend to try to distinguish attractors like these and these. We calculated then the average and dispersion of the attractors. With the average, you can distinguish these three attractors easily. In this case, they share the same average, but you could distinguish the attractors by the different dispersions. So in our case, we calculated between varying VAC and VDC. Oh, the image is not very good. But here we have the dispersion of the position and velocity. And if you had more than one attractor, what would you expect? We'd expect some jumps here. You don't have jumps. So our attractor is unique within this region. But here we consider the same initial condition. So we vary the initial conditions too. We have a grid with smaller resolution. Each point here corresponds to results of 200 different initial conditions. So if you had another attractor here, chaotic attractor has some jumps here, changes here, but you see that things change smoothly. So no jumps observed. So our evidence corroborates the hypothesis that chaos is robust within V. We have investigated another system, which is the Duffin oscillator. The case of double L Duffin oscillator. We have considered the case of one L too, but this is more interesting. You can have this equation simulated or generated by electronic circuits or mechanical systems like this. And the results are like this. Well, this is the case of a single frequency. You have some chaos here, but when okay, just ending like that. This is what you get when you add the second frequency. You have chaos almost everywhere. Okay? So you can get, so for applications, we have made a figure with very high resolution, 2,400 points here and 1,000 points of resolution here. Okay? And I have checked that this attractor is robust. This is we checked the uniqueness of the attractor. Again, we have no jumps here. Okay, for the same initial conditions with high resolution. And you have, I'm already finishing. And here, varying the initial conditions. Again, no jumps. So the attractor is unique. It varies smoothly. So you design your system to work here. It may suffer variations, but the attractor is approximately the same. Okay, so to conclude, I'm sorry for the delay. We have seen that we can, in principle, get robust K in the system, what's good for applications, but this is ongoing work. It would be interesting to respond to the question about the fundamental reasons behind the emergence of robust K in the systems. And it's important to investigate what other continuous time dynamical systems may display robust chaos under multi-frequency excitation, 2 or more. And it would be interesting to check this experimentally. Well, thank you very much for your attention.
Thank you very much. Time for maybe one urgent question.
Now that you have two frequency excitations, perhaps a way of getting rid of some of those nasty resonances would be to add one more, maybe a 3-frequency excitation. What do you think? We haven't tried
the smaller the number of frequencies you have to use to excite system, the better from the practical perspective, because you need to have an oscillator. That's a circuit that consumes energy. Okay, so if you get the result with the minimum of frequencies, the better. So if you get the result with 2 frequencies, that's good. But it's known that for the case of the Duffin oscillator, it's known that as you add more frequencies, you can lower the threshold for getting chaos. That's a theoretical result, but this doesn't say anything that you're going to get robust chaos. Just the threshold lowers. So as you add more frequencies, we can expect that we get better results.
The other possibility is, of course, to not fix the frequencies too precisely and allow for a little bit of noise on top of it. Yeah. Okay. So with this, I would like to close this morning's session. Thank you very much to you and all the speakers. We reconvene here at 2 p.m. for 2 more sessions.
Pode